Hello friend, myself Pankaj Patel, Professor in the Department of Engineering Mathematics, TIT Group of Institution. I will deliver expert lecture on numerical methods for solving transcendental equations. It is very important tool for researchers and scientists. Previously, where equation is of low degree, that is linear, or it is quadratic, or it is biquadratic, it can be solved by direct method. Direct method means analytical method in 2 or 3 steps. But what happens when degree of equation becomes higher or equation becomes transcendental? No direct method exists, and therefore we shall take the help of numerical method to find its solution. I am discussing important numerical methods. The name of method is Newton's Raphson method. This method is very important for engineers. It is capable of finding real as well as complex root. Other method can be used for finding only real root, but it helps us to find complex root also. If initial approximation x0 is chosen complex number. Let me tell you first of all what is the transcendental equation. An equation containing transcendental function, that is logarithmic function, exponential function, hypergeometric function, are known as transcendental equation. For example, we have equation e raised to x minus 2. We have equation log x minus 1.2 is equal to 0. We may have equation like 3x minus cos x minus 1 is equal to 0. These are not simpler, they need special technique to solve. Therefore, I have chosen transcendental equation. So, I will solve one of these questions by using Newton's Raphson method. In Newton's Raphson method, initial approximation x0 is required. We shall determine this x0 by intermediate value property. You can see in PowerPoint presentation, if x0 is initial approximation of the root of the equation f of x is equal to 0, then we can take x1 is equal to x0 plus h as an exact root. If this is an exact root, then f of x1 will be equal to 0, and by the help of Taylor series we can expand this in increasing power of h. So we will have f of x0 plus h f dash x0 plus h square upon 2 factorial f double dash x0. Since in this h is very small, therefore we can neglect h square and higher power, thus giving f of x0 plus h f dash x0 is equal to 0. From this we can calculate the value of h, and h is nothing but minus f of x0 upon f dash x0 as given in the PowerPoint presentation. Then our equation 1 becomes x0 minus f of x0 upon f dash x0. Now this approximation is much more closer than our initial approximation x0. Similarly, we can start from x1 and we shall get next approximation x2 by repeating same thing, and in general we can get xn plus 1 is equal to xn minus f of xn upon f dash xn. Now this can be used for finding solution of any question, whether it is transcendental or whether it is algebraic one. This I am using this concept, I am using this mathematical formulation for finding solution of 3x is equal to cos x plus 1. Now first of all in this question, we have to find initial approximation x0. This can be done by the help of intermediate value property. We shall find first of all interval in which root lies. So we have taken 1.0. Now at 0, the function is minus 2. We have also taken another point. At 1, the value of function is 1.45. As calculated, It is given in the PowerPoint presentation. So this indicates that root lies between 0 and 1. Now the interval is 0 and 1. We can take initial approximation within this interval from 0 to 1. But we should take care whether this initial approximation is closer to root or not. So we have taken initial approximation x0 is equal to 0.6. Then putting this x0 is equal to 0.6 in the formula of Newton's-Raphson method, we shall get first approximation x1. x1 is, as given in the slide, is equal to x0 sin x0 plus cos x0 plus 1 upon 3 plus sin x0. Now putting x0 is equal to 0.6 in this equation, x1 comes out to be 0.6072. And similarly, we can find x2 by putting x1 in the general equation of Newton's-Raphson formula. This x2 will be equal to 0.6071. Now we can see that x1 is equal to x2 up to 4 places of decimal. Therefore, the correct value of root is x is equal to 0.6071. So we can conclude that one of the real root of this equation is 0.6071. In the same question, if we have chosen x0 not 0.6, 0.5 or 0.4, then number of iterations will be more and time required will be more. So while using Newton's-Raphson method, we have to take care that initial approximation chosen must lie closer to the root. Then it will converge to the root more rapidly. This is the case in case of Newton's-Raphson method. Now how this method works faster, I will show by solving same question by another method. The name of that method is regular-Falsy method. Although regular-Falsy method converges to the solution always, but its rate is slower than that of Newton's-Raphson method. So here you can see on PowerPoint presentation, I have taken an equation f of x is equal to 0. This requires initial bracket of the root, means initial interval of the root. If f of x0 into f of x1 is less than 0, then this says that a root lies between x0 and x1. This is done by the help of intermediate value property, which I have not shown here. It is very small property. And if f of x0 into f of x1 is less than 0, then this indicates that graph of the curve y is equal to f of x crosses the x-axis between these points, indicating the root lies between x0 and x1, which I have shown in the figure given in the PowerPoint presentation. Now, what this method actually is, it consists in replacing the equation of the curve by means of chord and taking the point of intersection of x-axis and chord as an approximation to the root. So I have found the equation of chord AB. Equation of chord is nothing but equation of straight line, y minus y0 is equal to slope into x minus x0. Now at x is equal to x2, in the figure which I have already shown, y will be equal to 0. And putting the value of y is equal to 0 in the equation of chord, the formula comes out to be x2 is equal to x0 minus x1 minus x0 upon f of x1 minus f of x0 into f of x0. So this is the formula for finding solution by using regular-Falsy method. Now, if you want to carry out iterations further, then we have to check again condition f of x0 into f of x2 is less than 0. If this is less than 0, then further root will lie between x0 and x2. And then we can get next approximation x3. We will also get f of x1 into f of x2 is less than 0. Then root will lie between x1 and x2. For comparison, we have taken same problem as we did in case of Newton's-Raphson method. Our problem in Newton's reaction was 3x minus cos x minus 1. Here also in regular Palsy method we have taken same problem, 3x minus cos x minus 1. First of all, we have calculated interval in which root lies. At 0 the value of the function comes out to be negative. At 1 the value of the function comes out to be positive. It is 1.46 as given in this PowerPoint presentation. I have shown there. Therefore, this indicates that root lies between 0 and 1. Now, our bracket of root is 0 and 1. This is our interval of root. So, we have taken x0 is equal to 0 and x1 is equal to 1. Putting this value of x0 in the given function, it comes out to be f of x0 is equal to minus 2 and f of x1 is equal to 1.46. Using these values in the formula of regular Palsy method, we can get second approximation. Second approximation comes out to be 0.5780 up to 4 significant figures or up to 4 decimal places. Now, for carrying next iteration, we have to again check the condition in which root lies. So we have found f of x2. f of x2 comes out to be negative. Then this says that f of x2 into f of x1 is less than 0. So further it indicates that root will lie between x1 and x2 as given in the presentation. Thus, in the next approximation, we shall replace unwanted point. Unwanted point was our x0. So the next approximation x3 is equal to x2 minus x1 minus x2 upon f of x1 minus f of x2 into f of x2. And putting the values of f of x2, x1, x2 in this equation, it comes out to be 0.6059. Again we shall check the condition whether root lies in the interval or not. So we have calculated f of x3 and we have also used the value of f of x1. Now f of x3 and f of x1 is less than 0. This indicates the root lies between x3 and x1. And then similarly putting these values, we got x4 is equal to 0.6071. And similarly we have calculated next x5, this is 0.6071. And next 0.6071. So here x4 is equal to x5. x4 is equal to x5. So therefore our root is 0.6071. So here we have seen that in this regular Palsy method, it requires 5 steps. Whereas in Newton's reaction method, our root was obtained in 2 steps. So Newton's reaction method is faster. The rate of convergence of Newton's reaction method is quadratic, that is, it is of second order, and the rate of convergence of this method is lower, it is linear. One of the important points in this regular Palsy method is one of the point moves toward the solution and another point remains fixed. If this is the case and this is the curve, this is one point, this is another point, this is the position of the root. If one point moves toward the roots, then it will start moving toward the root and another point will remain fixed, as I have shown in PowerPoint presentation. So now I would like to conclude by solving this question, that in case of Newton's reaction method, when we have taken x 0.6, then our root was obtained in 2 iterations, means in 2 approximations, and that was 0.6071. And same thing, if x0 is chosen as 0.3 in the same Newton's reaction method, then number of iterations will be more and we will require 6 number of iterations, and that is time consuming. And in case of regular Palsy method, the number of steps which was required to get the solution was 5. So from this we conclude that Newton's Raphson method is faster than regular Falsy method, and if f dash x0 is not equal to 0, then we should use Newton's Raphson method to solve transcendental equation rather than this regular Falsy method. Although regular Falsy method converges to the solution always, but its rate of convergence is slow. Another point I would like to mention in the Newton's Raphson method, that initial approximation x0 should be chosen sufficiently close to the root so that it converges more rapidly to the solution. And in regular Falsy method, nothing such type of thing is required. So dear friends, whenever you get transcendental equation or higher degree algebraic equation, you can always use Newton's Raphson method rather than all those methods, rather than this regular Falsy method, bisection method or graphical method. These methods are very slow in comparison to Newton's Raphson method. There is another important method, secant method. The rate of convergence of secant method is 1.62, and this rate of convergence is quite faster than regular Falsy method. But secant method has drawback that it may converge and it may not converge always. So therefore, friends, take care for choosing x0, that is initial approximation, in Newton's Raphson method, and always choose Newton's Raphson method to solve transcendental equation or higher degree algebraic equation. Thank you.